time to do some more practice involving integration in polar coordinates, which really is mostly about the setup. The integration, no problem. Once we get the setup, life is good, and we can do all sorts of things. So make sure you're practicing setting things up. Take some time. And if you're following along with the video, make use of the pause button. If you see a problem, try it yourself first. Practice the procedures. Learn to get things set up, and then you'll become amazing. Amazing! I know you can do it. It's going to be wonderful. Well, let's begin. Our first problem. Find a constant c so that the volume for the set of points where x squared plus y squared is less than or equal to z less than or equal to c is 8. Now let's think about how we can interpret this problem, get an idea for what's going on. So we can think of it in the following way. We can say, okay, well, x squared plus y squared equals z. That's like a bowl. It's the elliptic paraboloid if you want to be very fancy. But of course, we're among friends. We don't have to be fancy. So you have the bowl here. It sits on the origin. And now, what is z equals c? Well, z equals c, like if I set z equals 0, that's the xy plane. Z equals c is just moving it up or down. So when we talk about z equals c, what we're talking about is a plane that's been shifted up some way. And you can imagine, all right, that hits here. And so in particular, what we have is, when we talk about our shape, it's like we have a bowl and we poured some sort of fluid in up to a depth c. And so we say, okay, that's our shape here, this part that's been filled. And now the question is, suppose we know how much there is. We know that there's 8. And all right, so we know that the volume is 8. Now the question is, what's the height? So how deep is it? All right, well, fun. See, in some sense, this is kind of like a reverse problem, because we have that the volume is 8. We know the volume. We don't need to find the volume. What we have to do is find the problem that gave us that particular answer. Now, the way we think about it, well, all right, 8 is the volume, and the way we integrate volume is we integrate over a region the height. So we need to think about what's our region, what's our height. Now, in some sense, the height, that's not so hard to figure out because we know where we're going between. We're going between x squared plus y squared, the bowl, and c, which is the top. So the height here would correspond to c minus x squared plus y squared. What's our region? Well, if we imagine going down, so what are we sitting on top of? Well, what we're sitting on top of is we're sitting on top of a circle. And in particular, if we want to figure out our region, we say, okay, when do these two surfaces, z equals c, x squared plus y squared, when do they intersect? So our region, R, this would be the circle, x squared plus y squared is less than or equal to c. So x squared plus y squared equals c is where they intersect, and then we want the interior. So all right, great. Now looking at this, we say, hey, this looks very polar because our region is a nice circle centered at the origin. Polar love circles centered at the origin. It's one of its favorite things. So we can say the following. Look, this is equal to the integral. And if we switch to polar, we got to switch our function. Because remember, every integral has three things. The function, how you split things up, and the region. So our function, c minus x squared plus y squared, becomes c minus r squared. The dA, that's an important thing. dA is r d r d theta. That's how we're breaking things up. r d r d theta. Now, we have to think about our bounds. Well, in terms of the picture in the xy plane, we have a circle here. and it's a circle of radius square root of c. So, okay, be careful. Not c, but square root of c is our radius. Now, for theta, where do we go? We go all the way around. So, the bound's there, 0 up to 2 pi. How about for r? Well, think of going from the center out to the edge. So we're going to go from 0 out to square root of c. And now we're ready to go. Okay, well, we can do a couple things. One thing is, the bounds are nice. See, the bounds are constants. You know, c is some constant. We don't know what it is, but it is a constant. We can actually pull this into two integrals and just do them simultaneously. 0 to 2 pi d theta, and integral 0 to root c of c times r minus r squared dr. Okay, well, the first one, really easy. If you integrate 0 to 2 pi d theta, well, that's okay. Theta from 0 to 2 pi turns out to be 2 pi. Now the second one, more interesting. So what do we have? Well, we integrate, we'll have, whoops, I wrote down r squared. It's r cubed, right? Because it's r squared times r. Yeah. So anyways, c times what? It'll be c r squared over 2. And here, it'll be r to the 4th over 4. And evaluate 0 up to square root of c. All right. Well, what goes on here? So we have 2 pi. Now when we plug in the square root of c, we'll get c times c. So c squared over 2. And then here, square root of c times square root of c times square root of c times square root of c. Well, you can compare things up. So we really end up with c times c, or c squared over 4. Well, okay, so you have a half minus a fourth, which is a fourth, then times by 2, don't forget that. So if you clean this up, you end up with 1/2 pi c squared. Now, remember, this is 8. So we rearrange. That says, hey, c squared multiplied by 2 divided by pi is 16 over pi. So we come to the conclusion, c has to be the square root of 16 is 4, and over the square root of pi, which is square root of pi. And we're done. Nice. Good. Okay, not so bad. A nice little warm-up problem. Get our multivariable calculus muscles going. Gotta always do, of course, a good warm-up. Now, let's try something else. All right. Find the integral 0 to 1, integral 0 to the square root of 1 minus y squared, sine of x squared plus y squared, dx dy. All right. Well, what do we have here? Now, you'll notice that a lot of these problems aren't telling us, oh, go into polar. We want to learn how to know when to go into polar. And there's, of course, problems that explicitly state, hey, switch to polar. But there's problems which are kind of hinting. And sometimes the hints are pretty loud. When you see things like x squared plus y squared featured prominently in the problem, that's a signal. X squared plus y squared is sending a signal saying, hey, you really should consider polar, because x squared plus y squared in polar is really beautiful. So, all right, keep that in mind. Let's talk about our region here. All right, so we're told, if we look at our bounds, our outer bounds say is y goes 0 to 1. Our inner bounds, well, 0 less than or equal to x, less than or equal to the square root of 1 minus y squared. Okay, well, this curve, x equals the square root of 1 minus y squared. Well, if you square both sides, x squared equals 1 minus y squared. Oh, this is feeling familiar. X squared plus y squared equals 1. Oh, feeling really familiar now. Say, hey, I think we have something with a circle here. More of a sign that we should be thinking about polar. So what do we know? Well, we have this bounding curve, that's a circle. We're told y goes from 0 to 1. Well, that's good. And x goes from 0 to the square root of 1 minus y squared. So that's how it's currently set up, if we think of it in terms of Cartesian coordinates. Again, circles are fantastic for polar. Aha, we say. Wonderful. Let's make a little bit of progress. And we can say, look, in polar, easy description. This is theta will go from 0, which is the x-axis, to pi halves, which is the y-axis. So as we move 0 to pi halves, we'll go along. And then r, well, we're going to start at the center and go till we hit the edge. Well, that says r goes from 0 to 1. So in other words, very clean bounds for polar. So everything's pointing to polar. So all right, we're in. We're in. We're all in. Okay, so this becomes integral. Our function will be sine of r squared. Now, dx, dy, this is how we break up our area. So that's our dA, our bit of area. Okay, so if that's our dA, in polar, dA is r dr d theta. So dx dy translates into r dr d theta. Now the bounds, well, theta goes 0 to pi over 2. Great. And r goes 0 to 1. Wonderful. And we're feeling pretty good. Now notice, because of that dA, there's an extra r here. See here, hopeless. But with that extra r being added because of the dA, hopeful. We can make progress. And so, all right, well, this integral again is one that you can break up. 0 to pi halves d theta. All right, and 0 to 1 sine of r squared r dr. Now the first one, very straightforward, that's pi over 2. Now here, what makes sense? Well, substitution. So we'll let u equal r squared. du is 2r dr. And we move the 2 across. And we're like, nice. So this integral, well, what would it become? 0 squared, 0. 1 squared, 1. We did actually check. We weren't just catching, 0 to 1, 0 to 1. No. Plug in the bounds. Check. Make sure. Because, the one time when you don't check is the one time something weird is going to happen. We don't want to fall into that trap. Then we have a half, because of that r dr becomes a half du. And then sine of r squared is sine of u. All right. Well, we can integrate that. That's minus a half cosine u. Don't forget the minus, and evaluate 0 to 1. So we end up with minus a half, and it's cosine of 1. Subtract cosine of 0. Cosine of 0 is 1. So we can actually put the minus inside, so make this a plus, make that into a minus. So 1 minus cosine 1. Don't forget there's a pi over 2 as well. So our final answer is pi over 2 times a half, making it pi over 4. And then 1 minus cosine of 1. And we're done. That's it. Wow, that wasn't so bad. It wasn't so bad because we switched into the coordinate system that made it easier to work with. The power of switching coordinate systems. It makes some problems easier. And after all, isn't that why we pretty much do everything in mathematics? We go out and say, hey, we want things to be easier. Of course. All right, well, let R be the region in the first quadrant with 1 less than or equal to x squared plus y squared less than or equal to 9. And find the integral of R of log of x squared plus y squared dA. Okay. Well, this will be fun. Let's see where we go. So we can see, look, our region is what? it's in the first quadrant, and it's between two circles. X squared plus y squared equals 1. All right? And x squared plus y squared equals 9. Now that's a circle not of radius 9, but of radius 3. So, all right, there we go. There's our shape. We can add a little bit of color here. And so now what? Well, certainly once you see a piece like this, you're like, look, this has got to be polar. Because it's so elegant to describe it in polar. And you would never want to say, I'm going to do this in Cartesian just because I'm stubborn. Don't be stubborn. Switch to this coordinate system that it's designed for. So we can say theta goes from 0 up to pi over 2. And then how about r? Well, we can say r goes from where? Well, we always think about coming out from the center. We start at 1, and we go to 3. So between 1 and 3. Great. All right. There we go. There we go. So now it's fairly straightforward, right? We can say, okay, integral. We have log of x squared plus y squared becomes r squared. And then, how about the dA? Well, that's r dr d theta. All right, that's no problem there. And let's see, what else do we have? Well, okay, our bounds. Where does theta go? 0 up to pi over 2. And how about r? Where does r go? 1 up to 3. All right, so there we go. And now, from here, it's going to feel really familiar. We could say, hey, this is the same as the integral from 0 to pi over 2 of d theta. All right, that's going to be something. And then we have this integral. Now, we could do various things. One thing we could do is do substitution. U equals r squared. du is r dr. We could pull the 2 down, have log of r times r, and do integration by parts. That seems tough, though. Let's not do that. Let's do substitution. Because we say, all right, this first part, this integral of d theta, pi over 2, life is good. No problem. Here, all right, if we let u equal r squared, then du is 2r dr. Well, okay, divide here. And, all right, half du is r dr. That's perfectly fine. And what happens next? Well, okay, this becomes the integral of, what do we have? Well, r equals 1, so as we go from 1 up to 9. And then we have a half log u du. Okay, now comes the moment. Do you remember the integral of log of u? And if the answer is yes, woohoo, then we're good to go. If the answer is no, all right, here we go. So the way we do the integral of log is we do it by integration by parts. So we're going to think about this first part. That's, I'll call it a capital U. And that's the part we don't know how to integrate, easy to differentiate. And the second part, our d capital V. So that d capital U is 1 over little u, d little u, and capital V is simply u. So you end up with capital U, capital V, u log u, minus the integral of capital V and capital du. Well, that's 1 over u times u du. Well, the u's here cancel, so it's the integral of just 1. So we really end up with u log u minus u, and then, of course, a plus c. So back to our problem. If we had remembered that, it's like, oh, yeah, that's how you integrate log. So we have, this is a half, and it'll be u log u minus u from 1 up to 9. Okay, when you plug in 9, well, that's a half, and then you have 9 log of 9, subtract 9. Then we're going to subtract, plug in 1. 1 times log of 1 is 0, because log of 1 is 0, so subtract a minus 1. And now, we're like, wow, that's great. Minus minus makes a plus, so really, this is like a minus 8 here. Don't forget that you have a half. So, put it all together. Pi halves times that gives us pi over 4. And then we have 9, log of 9, and minus 8. And that's it. That's the answer. Ah, great. Yeah, wow. Of course, you're probably thinking, my goodness, these all feel the same. Can't we try something different? Be careful what you hope for. Okay, here we go. Something different, right? Find integral 0 to 1, integral 0 to x, arctangent of y over x, dy dx. That's definitely different. Oh, my goodness, wow. Okay, so we need to think about this. It's not so clear that this is polar, right? It doesn't feel polar because we don't see x squared plus y squared. That's usually the thing we think about when we think of x squared plus y squared. And so you might say, well, what's suggesting polar? There's sort of a well-known fact that x squared plus y squared is equal to r squared, but there's a slightly less well-known fact that says, suppose you take y over x. What do you get? Well, if you think about y is r sine theta, and x is r cosine theta. So when you take the division, the r's cancel, you end up with sine over cosine, also known as tangent. So y over x is tangent theta. And then you're like, well, arctangent. So arctangent of y over x is acting like theta. Now, you might notice we put some quote marks. Now you're probably like, wait, why? Why are you doing that? So the reason we put some quote marks in there is you have to be careful. Now, arctangent of y over x is theta if we interpret it in the right way. The arctangent function only returns values between negative pi over 2 to pi over 2. But theta, of course, can go at any angle. So what happens is when we say it's equal to theta, well, it's really theta plus some multiple of pi. So you have to be careful. This is true as long as theta is within the right range. So negative pi halves, less than theta, less than positive pi halves. If theta is outside that range, not quite true. You have to add a pi. And so we have to think about where are we. So let's talk about our bounds. Well, for our bounds, we're told x goes from 0 to 1, and that y goes from 0 up to x. So the picture, well, okay, we have y equals x, here's x equals 1. So we have this triangle, and it's this triangle right here, where for x going from 0 to 1, we go up. For any value of x from 0 to 1, we're slicing in this way. So there's our region. Our region also doesn't suggest polar, right? Because there's no circles involved. Well, okay, we'll figure it out. We'll get there. We'll get there. So, all right. But because we say, hey, in this region, we're in the region where theta is between negative pi halves and pi halves. It's actually perfectly fine. There's nothing weird going on here. We're happy with this. All right. Well, good. Great, actually. And so let's see what happens. We're going to think of going to polar. Just the biggest thing is that the fact that we see an arctangent of y over x, and they say, oh, in polar, that's so clean. So polar seems a really good way to approach this. So we'll have a theta. Now remember that dy dx, this is our dA. which becomes r dr d theta. So we have an r dr d theta. And now we've got to think about our bounds. Okay, so let's start with theta. Well, it's not so hard to think about theta. We just have to think about, all right, where does theta go in this region? Well, we go from 0 up to the line y equals x, which corresponds to the angle of pi over 4. Okay, so that's great. So what about for r? Well, for r, what's going to happen is we're going to start at our center. So there's our center, and then we're going to go out till we hit that line. So we say, wonderful. We're going to start at 0. All right. And then we go out to this line. Now, here's the next challenge. What is that line? It's the line x equals 1. But I don't need an x equals, I need an r equals. Well, all right, x equals 1 is the same as r cosine theta equals 1, which becomes r is secant theta, because I can divide by cosine. So I'm going to run out all the way to secant theta. All right, good. Well, so we're going to go 0 up to secant theta. Now we're ready to begin. We set up our integral. All right. Well, this is an integral you can't pull apart because the bounds, there's functions inside of them. So you got to really do it one layer at a time, which means it's going to take a little bit of work. That's all right. We don't mind. We don't mind work. Okay, so what do we have? Put this down here. We have integral 0 to pi over 4. And when we integrate the first time, we're integrating with respect to r. So 1/2 theta r squared. Evaluate from r equals 0 to r equals secant theta and d theta. Well, plug in 0, you get 0. Plug in secant theta, well, you get secant squared. So integral 0 to pi over 4 of 1/2 theta secant squared theta d theta. All right, great. Woohoo! Nice. Now, where do we go from here? Looking at this, what do we see? Well, there's the secant squared, there's the theta. So it's kind of a mixture of polynomial and trigonometry. And when we see that, we usually say, okay, parts. So let's do some parts. Now, the good news is secant squared, that's not just any random function. It's one that has a nice antiderivative. So, which is good, because we'd really want to take a derivative of the theta, because that will make it essentially go away if we take one derivative. So we see, okay, we'll even throw in the half, just so we don't forget about it. So du is 1/2 d theta, and the antiderivative of secant squared is tangent. Okay, so what do we have? We're going to have u times v. So 1/2 theta tangent theta, and evaluate from 0 to pi over 4, whatever that turns out to be, minus the integral of v du. So that's the integral 0 to pi over 4 of 1/2 tangent theta d theta. Now, the good news is we can integrate tangent. The integral of tangent is log secant. So we have 1/2 theta tangent theta minus 1/2 log secant theta, and we can just say, look, we'll both evaluate them, 0 to pi over 4. And here we go. All right. Well, we plug in pi over 4. What do we have? We have 1/2 times pi over 4 times tangent of pi over 4. Well, that's going to simplify to pi over 8, because tangent of pi over 4 is 1. Minus 1/2 log of secant of pi over 4. Well, secant of pi over 4 is square root of 2. So we can write that as the square root of 2 there. And when we plug in 0, well, that's 0 times 0, all right. Secant of 0 is 1, but log of 1 is 0. And so that's it. That's it. So there we go. Now, we could do various things. For instance, log of square root of 2, because it's 2 to a power, you can bring the power down in front. We won't do that, but it could be done. But there we go. Wow. Cool. It's almost more amazing that we can get an answer than what the answer is. But it's also kind of a nice answer. Maybe not the answer we would have thought of when we started, but that's all right. It doesn't have to be the answer that we think of. It just should be the answer that it is, right? Whatever the right answer is, that's what we want. Wow. Fun problem. Good stuff. Good. That was nice. Okay, well, let's try another one. Okay. Let R be the region where the square root of y squared is less than or equal to x, is less than or equal to the square root of 1 minus y squared. Find the integral over this region of x over x squared plus y squared plus 1 dA. Okay, that's interesting. Now, just looking at the function, we see, x squared plus y squared. That's a nice hint. Polar is a reasonable thing to be thinking about for this problem. Let's talk about our region. Figure that out. Now, another name for the square root of y squared, this is also known as absolute value of y. So we're told that x is bigger than or equal to absolute value of y. Now, maybe we're not quite so familiar with that. We are familiar with y equals absolute value of x. It's that classic V shape. So x equals absolute value of y will be that V which opens to the side. So I think it opens this way, right? Yeah. So if we sketch, we see, okay, all right, that's not so bad. So we have x equals absolute value y, and we're told, look, we've got to be above that. So if x is above, that means we're to the right. But we also have this other curve, square root of 1 minus y squared. Well, if x equals square root of 1 minus y squared, if we square both sides, x squared equals 1 minus y squared, or x squared plus y squared equals 1. It's a circle of radius 1. Circles, oh, polar, oh yeah, oh yeah. Can you feel the polar curve today? Doo-doo-doo. Okay, good. So now we have this x squared plus y squared equals 1. And we've got to be to the left. So we say, okay, that says our region that we're after is in between these two. And when we look at it, we say, boy, you know, it wouldn't be the cleanest to do in Cartesian coordinates. We'd have to split it up to two integrals. Whether we integrated where we sliced horizontally or sliced vertically, we'd have to do at least two integrals. And they wouldn't be the most pleasant looking integrals to do. But we're not going to do that, right? We've already sort of said, look, we're committed. We're going for polar. We're going to put our money in the idea, invest, that polar can actually help us. So, where to from here? Well, looking at this, we say, what's the description in terms of polar coordinates? In other words, in terms of r and theta, what does this region become? Well, for theta, we think of, we start down there, and we're going to swing around to up there. So, where does our angle go between? Well, this angle coming down corresponds with theta is negative pi fourths, and this one coming up is theta is positive pi fourths. So we say, aha, negative pi fourths less than or equal to theta less than or equal to positive pi fourths. Now that's just for theta. For r, start at the center and go till you hit the edge. And where we're hitting is the circle. So it's a circle of radius 1. So 0 less than or equal to r less than or equal to 1. These are some nice bounds. We definitely approve of these bounds. All right, well, great. Now we just have to say what's our integral become. So we're going to have integral x. Well, x is r cosine theta. Okay. X squared plus y squared, r squared, plus 1 is plus 1. dA is r dr d theta. All right, and then our bounds. We have theta goes negative pi over 4, positive pi over 4, and then r goes 0, 1. And there we go. That's the setup. But of course, we're not satisfied with just setting it up. We want to actually get the answer. All right, so in this case, the bounds are nice. They work with us. So we can really pull into two integrals. So we have, all right, there's the integral negative pi over 4, positive pi over 4 of cosine theta d theta. And then there's integral 0 to 1 of r squared over r squared plus 1 dr. All right, well, we have to work through these. Now, how can you do the second integral? I think that one might be the more challenging one. And if you go back to techniques that we often do in Calculus 2, you would say, oh, this is partial fractions, do some long division, But there's something a little bit simpler to notice. Notice that the top is very close to the bottom. They're almost identical, right? What's the difference? Plus 1. So let's do something. This really cool idea. It's called add 0. In our case, our 0 looks like plus 1 minus 1. Well, plus 1 minus 1 is equivalent to 0. So why does that help? Well, think of it now as two pieces, r squared plus 1 and minus 1. So if we think of those as our two pieces, r squared plus 1 over r squared plus 1 is 1. And then you have the 1 over r squared plus 1. This is what we've secretly done, although we didn't say it out loud, is we did long division right there. All right. Shh, don't tell anybody. We're among friends. All right, here we go. Let's integrate. Integral of cosine, positive sine. All right, and then we're going to go from negative pi fourths to positive pi fourths, whatever that turns out to be. And over here, in the meantime, we're going to get r, because integral of 1 is r, and minus integral of 1 over r squared plus 1, arctangent. All right, good. And we're going to evaluate that, 0 up to 1. Whoops. All right. So, well, sine of pi fourths is root 2 over 2. Then we're going to subtract. Sine of negative pi fourths is minus root 2 over 2. So these don't cancel. They actually combine. So when we put them together, it's really adds up to a single root 2. So that's that part. In the meantime, over here, well, we have 1 minus arctangent of 1 is pi fourths. And then if we subtract 0, well, 0 and arctangent of 0 are both 0. So that's great. So this part becomes root 2. This part becomes 1 minus pi fourths. So our final answer is what you get when you multiply them together. Square root of 2 times 1 minus pi over 4. And we're done. Wow. Wow. What an interesting answer. I don't think it's so clear, how does square root of 2 show up? Because there's nothing here that says, oh, hey, there's a square root involved in this problem. And yet, there it is in the answer. So, wow, good stuff. This is a fun one. I like this one. Of course, I like a lot of problems. Well, yeah, you see I chose the right profession, right? If you love what you do, you'll never work a day in your life, as they say. And mathematicians, we tend to love what we do. All right. One more. And this one is super special. Really, really. We're going to walk away from this one thinking, oh my gosh, we're going to be on cloud 9 when we see the answer to this. Because for one thing, okay, what is it? All right. Find the integral from negative infinity to infinity of e to the negative x squared dx. And our reaction is like, what? First off, if you've been hanging around calculus for a while, we keep saying, you can't integrate this. By which we mean there's no antiderivative of this. And there's not. There is no antiderivative of this. And it gets even more strange because this is a single variable integral. What is it doing here in multivariable and multivariable with polar? What? Crazy. Crazy. Okay. So we're actually going to find this integral. And if you haven't seen the value for this before, I think it might surprise you when we get to the end. All right, so how are we going to get there? Let's suppose for a second, let's call this L. So we're trying to find L. Now, I'm going to do something rather strange. And I want to say some of the steps that you're about to see aren't necessarily the most intuitive. So don't feel like, how would I have come up with that by myself? If you do, that's amazing, fantastic. If you don't beat yourself up about it. Enjoy the journey. It's a beautiful journey we're about to do here. So instead of finding L, we're going to find L squared. Now the good news is this function is strictly positive. So once we find L, we take the square root. There's no ambiguity. There's no plus or minus. We know it's whatever the positive part is. All right. Well, what is that? Well, that just says take 2 copies. Okay. Well, that's no big deal. Now, at this point, you're like, this doesn't seem like very helpful at all. It seems like you're just going to do 2 impossible things at the same time. Now, here's the next thing. And you'll either just completely accept this at face value, or you might have to think about it for a second. I claim, hey, one thing we can do is just change the name of one of the variables here. So let's take our second one, and instead of having it be e to the minus x squared dx, make it e to the minus y squared dy. Now, you can do this in a couple ways. You can argue, this is a substitution, y equals x. Or you could just say, it's just a variable name, right? Changing names doesn't change the problem, doesn't change the answer. So it's the same. Now, if you've been following along with the practice, you've seen there are times when we pull things apart. We can push things together. And because they have different names, there's no ambiguity. See, we wouldn't want to push these together because they have the same name. What? That doesn't make any sense. But since they have different names, let's push in. So we have integral minus infinity to plus infinity, integral minus infinity to plus infinity. Then it'll be e to the minus x squared, e to the minus y squared, dx dy. Or integral minus infinity to plus infinity, integral minus infinity to plus infinity, e to the minus x squared plus y squared, dx dy. And now we're like, okay. At least there's starting to be a hint of polar. X squared plus y squared. That's our big clue that polar could be entering into the formula here. So we're like, cool, awesome. This part here will become r squared. Well, that's no problem. Great. Dx dy, that'll become, that's our dA, right? That'll become r dr d theta. What are the bounds? Okay, so let's sketch. First off, if we sketch the region in the plane that we're currently integrating over, so here's our plane. What region in the plane are we currently integrating over? Well, we're integrating over the whole plane. It's everything. All right, so what will the bounds be? How do you describe the whole plane? What we're going to do is say, well, theta is going to go full revolution all the way around. And then r goes from where? Well, you start at 0 and you keep going all the way out. So go to infinity. Technically, it should be a strictly less than because we can't equal infinity, but all right, we're among friends. Okay, now you might pause for a second and say, are we justified in some of these things? We have all this infinities involved. Are we okay? Yes, you're okay. It's perfectly fine. We can go back and talk about, well, as things head towards infinity and yada yada. But everything's perfectly fine. No worries. So let's switch to polar and see what we get. So here we go. We have all our pieces. Integral e to the minus r squared. And then there's going to be an r dr d theta. Well, theta goes 0 to 2 pi, and r goes 0 to infinity. We can pull these integrals apart because the bounds are nice. They don't rely on each other. So, all right. So we have, this is going to be integral 0 to 2 pi d theta and integral 0 to infinity e to the minus r squared r dr. Now the first integral, okay, that's easy, 2 pi, no problem. The second one, a little bit more interesting. Do a quick substitution. Suppose you let u equal r squared. Du would be 2r dr. All right, move the 2 across. That's a half. Du is r dr. So that what would happen is, all right, you have the 2 pi from here. Okay, there's our 2 pi. Now here, we're going to have the integral. And we're going to go 0 to infinity. Because we plug in 0, we get 0. As we go to infinity, we go to infinity. And when I talk plug in, I'm talking about plug in values for r. And then we have e to the minus u. And then the r dr becomes a half du. All right. Now, what happens with our 2's? Ha ha ha. Cancel, cancel. Nice. Okay. Well, we're making progress. Okay. So this is pi, because of that pi, integral e to the minus u. Well, that's minus e to the minus u. Evaluate 0 to infinity. And now we say, okay, plug in infinity. Well, that really means as we go to infinity, what happens? And as we go to infinity, it gets small. It goes to 0. Plug in 0, you get e to the minus 0, g to 0, which is 1. So we end up with pi times 0 plus 1. The 0 from the infinity, 1 from when we plug in 0, or pi. Now remember, that's not our answer. That's the square of our answer. L squared is pi. So finally, we take the square root, and lo and behold, we can say this is the square root of pi. I think this is amazing, because when you look at the integral, it says this has nothing to do with circles. No pi should be involved. And then you see the answer, and it's like, there's a pi! What? Crazy! Wow! Amazing. Amazing. And by the way, this is why if you go into statistics, why you see a square root of pi showing up. It's because this integral involves the square root of pi. So they have to put it in there so that things work out numerically. Wow, what a nice and beautiful answer. In an unexpected place where polar coordinates show up to help us find what it should be. A great way to end our session. I hope you had fun. I know I did, and I hope to see you again. Bye.